FBD, free body diagram, shows all the forces that are applied to an object. Now, the object in this case is the knot, this thing right there. So I draw XY axis, and then I just draw the forces that they gave me. Okay, that's T1, T2, and T3. Alright, you gotta realize I always want the angles on the slanted forces drawn from the x-axis. So what would that be? Let's look at this picture right here. What would this angle be right there? Well, if you recognize the theorem of geometry that states that if you have a line connecting two parallel lines, the parallel lines being these two, alternate interior angles are equal. So on either side of that diagonal that is drawn between these two parallel lines, those angles have to be the same. So that angle right there is 60 degrees as well. Okay, so there's my free body diagram. Okay, letter B. What is the size of T3? Well, if you look at T3, it is equal and opposite to the tension in the rope that's applying, that is supporting the weight. And because that weight is not accelerating up or down or sideways, the weight of that block is equal to T3. So weight is M times G. The mass is 5 kilograms. G, acceleration due to gravity, is 10. So I can say that the weight is equal to T3. And so right here is 50 newtons. What is the value of the Y component of T2? Okay, I don't need to do that. There is no Y component of T2. I really meant to ask right here. I meant for that to be T1. I meant for that next one to be T1. And I meant for this one to be T1 as well, letter E. Okay, so that was a typo on my part. So what is the value of the Y component of T1? Okay, well, first of all, hope you remember what Y and X components are. I'm going to just draw a rectangle with the given slanted force, diagonal force, as the diagonal from one corner to the other corner of that rectangle. And so this would be right here. That would be T1 Y. And this guy is the horizontal component of T1 X. Okay, next, what is the value of the Y component of T1? Okay, that's T1Y. Now, if you look at a free body diagram, that T1Y has to be balanced by T3. So it equals T3, which we have as 50 newtons. If it wasn't balanced, then that knot would be accelerating up or down, but it's not. It's just at rest. So the net force would be 0. So the vertical forces have to cancel out, balance each other. Okay, calculate the size of T1. Okay, now that I know Ty, I can do T1y equals T times sine of theta. I'm solving for T1. Okay, that's on your equation sheet as qy equals q sine of theta. So let's plug in our values. T1y I just found it. So 50 equals T1 times sine of 60. So T1 is equal to 50 divided by sine of 60, which equals 57.7. I'll just say 58 newtons. Okay, going on. Calculate the x component of T1, so T1x. Well, look on your equation sheet. It's just trig. That's T1 times cosine of theta. Simply put q's in for T1s. Okay, so I'll just solve that. I have T1 now. So that's 58. Remember, I just found T1 times cosine of 60. That equals 29 newtons. Okay, so now let's figure out what T3 is. I'm sorry. I meant, let's figure out what T2 is. I got these numbers mixed up, I guess. So T2, if you look at this free body diagram, there's only T1x and T2, and they balance each other out because it's not accelerating sideways. So we can say that T2 is equal to T1x, which we just found, 29 newtons. Okay, so we just completed that problem. Okay, for this problem, it's similar, but we got two slanted forces instead of just one. So let's draw the free body diagram showing the x and y components. Okay, so here we go. Make a cross. This guy is the knot. We got T3 pointing down. And from what we talked about in the first problem, we know already that T3 equals the weight of the block. By definition, weight is m mass times acceleration due to gravity. So that would be mass is 5 kilograms times acceleration due to gravity is 10. So T3 is the weight, which would be 50 newtons. Okay, now if this block is hanging in the middle of the string, then both these angles have to be the same. And if both those angles are the same, then we can assume that these two tensions are equal, but, not in the same direction, equal in magnitude. So here's T2, and here's T3, no, T1, sorry. And because what we said before, remember, we want the angle from the x-axis, so these are alternate interior angles. So this is 37 degrees, and this is 37 degrees, right? Just like we said before. Okay, so they want me to draw the x and y components, so this is going to really kind of mess up my picture. So let's draw a box around each one of these. Okay, and then you draw use a 3-finger rule. Okay, so that's T1y, that's T1x. And over here, I'll do the same thing. Okay, so that's T2y, and that's T2x. Now, you should be able to see that these, because T1 equals T2 in magnitude, and they're the same angle, the y components of these two forces had to be identical, and the x components had to be identical. Okay, so I already solved that one. I did that in the picture, part A. Part 3. T3 must equal the sum of the y components. So I'm just saying T3 has to equal T1y plus T2y. Okay, why? Because it's not accelerating up or down. It's at rest. The whole system is at rest. So that means the net force in the y direction is 0. That means the y forces, the vertical forces, must balance out. Okay, so solve for T1y. Well, look at this picture. T1y plus T2y equals 50. And these two guys have to be exactly the same, because the forces that the y components are, T1 and T2, are identical. So really, each one has to be each one of them is half of the 50, because T1y equals T2y. We can say that T1y equals 50. So T1y equals 25 newtons. And because of what we just said over here, so there's T2y equal 25 newtons. Each of them take half the weight. Just like when you're on a swing. If you're on a swing, sitting on a swing, here's you sitting on a swing. Your weight is cut. The tensions in both the chains equal if you're in the middle of the swing, and each of those tensions must equal each other, and both of them equal the weight. So 2t equals the weight. T equals the weight divided by 2. Okay, calculate the magnitude of T1. T1 is the same thing as T2, like I just said. So, we're going to have to solve for either T1 or T2. Okay, so use trig. I have the y component, so I can do T1y equals T1 times sine of theta, using the qy equals q sine of theta equation on your equation sheet. So I got T1y, it's 25. I don't know T1, sine of 37. So T1 equals 25 divided by sine of 37, which is 41.5. I'll just round it off. 42 newtons. So I really don't have to do this part because my objective is to find what T2 is. And so I don't need to find the X components. I can, but who needs to? We don't. So what's the magnitude of T2? T2 equals T1, which we just found to be 42 newtons. Okay, let's do this problem. Okay, we got two objects. Okay, so it's like number one. It's like what we did in number one. But there's two of them, two things hanging, like the one in number one. So we got to do them separately. So first of all, let's draw the free body diagram right on the picture, okay? So this is the knot. There's T4, and from what we said before, the weight is mg is 80 newtons. So T4 has to be 80 newtons on the block. Okay, we got T3. I don't know what that is. Then we got T2 pulling back at it. Let's label it. Okay, we got the angle already. Okay, on the other side, we got T5. We know that one is the same as the weight, which is mg, which is 12 times 10, which is 120 newtons. So we know the tension on this knot is 120 newtons. Okay, T1 goes this way, but I don't know what the angle is either. But pulling this way is T2, and it's exactly the same size as the tension pulling on the other one. These two are the same because of Newton's third law of motion. When you pull a string, there's a pull back on either side of the string. They oppose each other. Okay, so there. Just do number one and number two. Okay, find, okay, letter C, find T4. Okay, I did that. I found T5. We did that already. Same as the weight. Find the y component of T3. Okay, so I'll draw a little triangle. Okay, remember this is like an XY axis. Okay, so here's that is T3, running out of space. That's T3Y. This right here is T3X. So what are we looking for? The Y. Now, can you see that T3Y is going to equal T4? Because that knot is at rest. There's no vertical acceleration. So T3Y has to equal T4. Which equals 80 newtons. Now find T1Y, okay? T1Y. Okay, well, first of all, we need to draw the X and Y components of T1. So right here is T1Y. Right here is T1X. So T1Y obviously has to be what? T5. Same like what we did. that equals 120 newtons. Okay, the next thing I really want to do, I got these out of order. After I did letter F, I want to go over here and change that to letter G. So T3. Okay, so I'm trying to find T3. I know T3Y. This one, and I know the angle, 25 degrees. So I can use a trig equation. So T3y equals T3 sine of theta. Again, that's on your equation sheet as QY equals Q sine of theta. So T3y is equal to 80. T3 I'm solving for, then sine of 25. So T3 equals 80 divided by sine of 25. So that comes out to be 189.2. So 189 newtons. Okay, now we're going to find T3x. So let's call this letter H. Okay, let's look at our diagram. Okay, so T3x. Well, since I have T3, I can, in the angle, I have T3, in the angle 25 degrees, I can find the x component of T3. So that's T3x. So T3x is equal to T3 cosine of the angle. So T3x is equal to T3, which is 189. We just found that, times the cosine of 25 degrees. That equals 171.29 newtons. So next, let's call this letter I. Let's find T1x. So look at the diagram. T1x is this piece right here. The x component of T1, which I don't know. I don't know T1 either. But look at this. This traffic light, this 12 kilogram traffic light is not moving. So the tension, T2, is the same as T1x. And the tension on the right side, right there, on the second traffic light, is equal to the tension on the first traffic light. And because the first traffic light is not moving, we can say that T2 equals T1x. No, T3x. T2 equals T3x. So therefore, we can conclude that what are we looking for? T1x. T1x is equal to T2 is equal to T3x, which we already found. Okay, so let's fill that in. So T1x equals T3x equals 171 newtons. And like I just said, T2, which is the tension, T2 equals T3x equals T1x. All that equals 171 newtons as well. So now, to find T1, okay, let's just review where T1 is. Okay, T1 is this force right here. Now, I can't use trig because I don't have the angle, which I have to find after I find T1. So, but I have the x and y components of it, right? We got T1y right here. We got that. That's 120 newtons, same as T5, the weight of the thing. And we just found what T1x is. So we can use those two, T1x and T1y, in Pythagorean theorem to find the hypotenuse, T1. So let's do that. And so that's letter K, really. So to find T1, I got to use Pythagorean theorem. T1 equals the square root of T1x squared plus T1y squared. So that equals, what's T1x? We just found it. 171. And T1y is 120. So I calculate that to be 209 newtons. And then finally, HHAKL, let's do letter L. Find angle theta. So, angle theta equals inverse tangent of T1y over T1x. So, inverse tangent of 120 over 171. That equals 35 degrees. Okay, so let's look at the next problem, which is number 5. Okay, the tension in this string is 40 newtons. We'll call that T. The coefficient kinetic friction, okay, that's not kinetic friction, that's the coefficient of kinetic friction, equals 0.3. Draw a free body diagram. Okay, well, the object's moving to the right, so the friction will be to the left. Lowercase f for friction. So let's just draw that. Okay, the box, I'll make a little circle in the origin. Okay, 40 newtons. That's what T is. Okay, it's 24 degrees. We got friction that way. We got the weight pointing down. And of course, we got normal force because it's on a surface. Now, important to realize, normal force is not going to equal the weight like it has been in the last test. Except that in the problems where it was an elevator accelerating up or down. Okay, so in this case, there's a diagonal force pulling up on the object. Well, part of that diagonal force is lifting the object slightly. Not off the ground, but off the scale a little bit. So, remember, normal force is scale reading. And so the scale's going to read less than your weight if someone's pulling up on you. So I'm going to draw the normal force as a smaller arrow than the weight. So let me just remind you, N is less than the weight. Okay, so there's my free body diagram. Okay, find the x and y components of the tension. Okay, so Tx equals T cosine of theta. I'm just using Qx equals Q cosine of theta. It's on your equation sheet. So Tx is 40 times cosine of 24. And then Ty is equal to T sine of theta equals 40 sine of 24. Okay, so I just calculate those. Calculate the normal force acting on the box. Okay, so I'm looking for N, the force, normal force. So, look, first of all, I forgot to draw the x and y components. I just went right into it. So there, draw your rectangle, and that's Tx, and there will be Ty. Okay, I just found Tx and Ty. Okay, so normal force. Okay, normal force would be that right here, right? Okay, so because the block is not coming off the ground, this is being pulled forward and upward, we can say that the vertical force is balanced. So we can say N plus Ty, the upward pointing force, is equal to the downward pointing force. So normal force equals W minus Ty. If I rearrange that, the weight is mg, right? So here's the mass, 8 kilograms. So the weight is mg, 8 times 10. 10 is the acceleration due to gravity, 80 newtons. So this be 80 minus Ty, which we just found, 16. 64 newtons is the normal force. Okay, it is not equal to the weight, which is 80 newtons, because the upward force. Okay, calculate the kinetic friction on the box. Well, they gave you the coefficient of friction is F over friction over normal force. So I'm solving for friction, so let's just rearrange it right now. The coefficient of friction is 0.3 that was given. The normal force is just found at 64. So 0.3 times 64 is 19.2. Calculate the net force on the box. Well, there's two net forces. The net force Y is 0 because those forces balance out. The net force X, well, let's look at that now. So I'm just looking at the horizontal forces now. There's only two of them, Tx and F. Okay, so Tx is going to equal, we already found that to be 37. And the friction we just found to be 19. So which one's bigger? Tx or friction? Tx. 37 is bigger than 19. So it'd be the Tx, the x component of the tension, minus the friction, which would be 37 minus 19. Okay, 37 minus 19 is 18 newtons. So calculate the acceleration of the box. Okay. Net force equals ma. We're doing x, of course. So 18 equals the mass, which is 8. Don't put the weight in, times a. So acceleration is 18 divided by 8. 2.25. So I'll just say 2.3 meters per second squared. Okay? Now, this last problem is just like that first one, except that the push is downward instead of an upward pull. So that makes it a little different in one little way. So let's draw a free body diagram. Okay, here's the XY axis. There's the box, that dot. We got friction pointing that way. We got normal force pointing up. We got weight pointing down, a gravitational force. Okay, now, do not draw your push like this. Don't draw it like that. You're supposed to always draw the arrow, the force vectors, the arrows, away from the box, from the object, in this case the box. Have the tail of the arrow always touching the box, the object. So let's draw it right. So right here is the push. I'll call that the applied force. Okay? And that's 20 degrees right there from the horizontal. Okay, now, if someone's pushing you downward and you're on a scale, what's the scale going to read? The scale reads your normal force. If someone's pushing you downwards at an angle or directly downwards, the scale's going to read more than your weight. So I have to realize that N is greater than the weight. Again, because someone's pushing down on you. So your weight doesn't change, the scale reading changes. And the scale reading is what we call the normal force. Okay, so there's my free body diagram. Okay, so let me draw the X and Y axis components of the slanted force. Okay, so there's the Y component and there's the X component. So let's call that AX, AY, the downward component of the applied force, the push. Okay, find the weight of the box. That's easy, mg. Now, if they gave me newtons, that would be the weight, but they gave me the mass, so it's 35 times 10 equals 350 newtons. Find vertical and horizontal components of the applied force. So that would be A, Y, AX. AY is A sine of theta. AX is A cosine of theta. So A is, the push is what? 500 newtons. I didn't write that. So AY is 500 times sine of 20. Whereas AX is 500 cosine of 20. Those equations in the Q form are on your equation sheet. So those are the calculations right there. Now, find the normal force acting on the box. Okay, now look at the free body diagram right there. So in the free body diagram, look at the vertical forces. Just look at the vertical forces. So we have normal force, the y component of the applied force, and the weight. Okay, so to find the normal force, we know something. We know that the net force is 0 in the y direction. There's no vertical acceleration. So what we have is the forces that point up have to equal all the forces that point down, the sum of the forces pointing down. So in this case, n's all by itself. There's no other upward force. So normal force is equal to the y component plus the weight. Okay, the weight's 350. The AY is 171. So you get 521 newtons. So look, 521 is bigger than 350 because someone's pushing down on you at some angle. Okay, so finally connect friction between black and ore. Okay, well, like we did in the previous problem, F equals mu times N. Mu is given in this problem as 0.52. And normal force is not the weight. It's what I just found it to be. So friction is going to be 0.52 times 521 equals 271. Now find the net force acting on the block, on the box. Well, the net force in the y direction we already found was 0, but in the x direction there's only two forces, friction and ax, and probably, let's see, ax, what's ax equal? We already found that, 470. And then friction equals 271. So all I do is, because they're opposing each other, subtract the smaller from the bigger one. So the net force in the y direction is the bigger one, which is applied force x, minus the smaller one, which is friction. So that'd be 470 minus 271. Equals 199 newtons. So that's the net force. Therefore, let's find the acceleration. Then we're done with this first section. Okay. We can use kinematics, but we're not doing kinematics. I don't have enough info, so I'm going to use the second law of motion, the law of acceleration. So F net is 199. The mass is 35. So A equals 199 divided by 35. I'm getting 5.69. So 5.7 meters per second squared is my acceleration. Okay, so this will take you up to Positive Physics Unit 8. Okay, but don't forget, Unit 8 and Unit 9 are on the next test. So